Hello friends, welcome back to my YouTube channel. In this class I am going to discuss three more problems of chapter 7 of PKNAG's Engineering Thermodynamics. And these problems are based upon the concept of entropy. Before starting I must say one thing to all of you, please do subscribe to this channel and of course like it and share it to your friends. Let's get started. The question number 7.28 is like this. So that if two bodies of thermal capacities C1 and C2 at temperatures T1 and T2 are brought to the same temperature T by means of a reversible heat engine, then ln T, natural logarithm of capital T, is equal to this much. We have to prove this expression. That means we have to express the common temperature T in terms of T1 and T2, of course in logarithm terms. So you see there are two bodies of thermal capacity C1 and C2. This body's thermal capacity is capital C1 and the initial temperature of this body is T1 and it is brought to a final temperature of T by operating a reversible heat engine. So a reversible heat engine will operate between these two temperatures, two bodies. This is the second body whose temperature is T2 and it is also brought to the common temperature T, and this heat capacity of this body is capital C2. This one is of capital C1, that is the heat capacity of body 1 is capital C1. Heat capacity is nothing but the product of mass and specific heat. A reversible heat engine operates between these two temperatures, work producing device. So let heat supplied from this high temperature body to the heat engine is Q, and W is the amount of work that is produced by this heat engine. Of course, a reversible heat engine works in a reversible manner. So this will be definitely Q minus W. So you see, since this is a reversible heat engine, all the processes executed by this heat engine are of reversible nature. So according to principle of increase of entropy, for reversible process, delta S of universe is equal to 0. According to principle of increase of entropy, this delta S of universe is greater than or equal to 0, and of course is equal to 0 for reversible process, since in the question it is given that a reversible heat engine operates between these two finite temperatures. So obviously delta S universe will be 0, and here delta S universe consists of three delta S terms. One is for delta S of body 1 plus delta S of heat engine plus delta S of body 2, and summation of these three delta S terms will be 0 because the heat engine is reversible one. So from this you see delta S of body 1 is nothing but, you see, delta S of this body 1. Delta S of body 1 is C dt upon T, and initial temperature is T1 and final temperature is T. So this is of course C ln T upon T1. C ln T upon T1. Similarly for body 2, the change in entropy will be integral of C dt upon T. Initial temperature is T2 and final temperature is capital T in both the cases as given in the question. Both are brought to the same temperature T by means of a reversible heat engine. So common temperature is, final temperature is same for both two bodies, and that is capital T. So this becomes C ln T upon T2. So now if you put all these values in this equation, this is always 0 because heat engine is a cyclic device and cyclic integral of any property is 0 and S is a property, entropy is a property of system. So this term is going to be 0. So from now delta S1 plus delta S2 is equal to 0 or C ln T upon T1 which is the delta S of body 1 that we have calculated, and delta S of body 2 is nothing but C ln T upon T2. So this is equal to 0. This is equal to 0 or so this is in fact C1, this is C1, this is C2 or C1 ln T minus ln T1 plus C2 ln T minus ln T2 equal to 0 or C1 plus C2 ln T equal to C1 ln T1 plus C2 ln T2. From this ln T will be, from this expression ln T will be C1 ln T1 plus C2 ln T2 divided by C1 plus C2. So C1 ln T1 plus C2 ln T2 divided by C1 plus C2. So this is the expression for ln T in terms of ln T1 and ln T2, and this is what we are required to prove. So this is the expression is proved now. So question number 7.29. Two blocks of metal each having a mass of 10 kg and a specific heat of 0.4 kilojoule per kg Kelvin are at a temperature of 40 degree Celsius. A reversible refrigerator receives heat from one block and rejects heat to the other. Calculate the work required to cause a temperature difference of 100 degrees Celsius between the two blocks. So suppose this is block 1, which is at temperature, suppose initial temperature of T, and this is a second, this is the second block, block 2, and the temperature of this block is also T because two blocks of metal each having a mass of 10 kg and a specific heat of this amount 0.4 kilojoule per kg Kelvin are at a temperature of 40 degrees Celsius. So here both are having the same temperature of, suppose this is capital T is 40 degrees Celsius. In terms of Kelvin this is 313 Kelvin. A reversible refrigerator, which is a work consuming device, operates between these two temperatures. So refrigerator always takes heat from one body and releases it to the other body. Suppose this heat taken from this body is suppose Q, and this is a work consuming device. Let W be the work input to this refrigerator. Then according to the principle of first law of thermodynamics or principle of conservation of energy, or you can say principle of energy balance, if this is Q and this is W, then this will of course be Q plus W. So obviously once heat is taken away from this block, its temperature will decrease and its temperature will increase, and it is given in the question that at the final state there is a difference of 100 degrees Celsius between these two blocks. Temperature difference of 100 degrees Celsius. So, and 100 degrees Celsius temperature difference means 100 Kelvin. Temperature difference is also 100 Kelvin. So, if the final temperature is let in this for block 2 is T dash, of course, final temperature of this block will be higher than the final temperature of the block 2 because the heat is supplied to it, and in this case heat is released or heat is rejected from this block. So, this will be obviously T dash plus 100 because finally there will be a temperature difference of 100 degrees Celsius. 100 degrees Celsius temperature difference means the same will be the temperature difference if it is expressed in terms of Kelvin. So, if it is T dash means this will be T dash plus 100 Kelvin. So, now mass is given 10 kg, C, small c, that is specific heat is 0.4 kilojoule per kg Kelvin. So, all the processes are reversible because it is given that a reversible refrigerator operates between these two blocks, reversible refrigerator. So, since all the processes are reversible means according to principle of increase of entropy, delta S of universe is equal to 0. That means delta S of block 1 plus delta S of block 2 plus delta S of heat engine is equal to 0. According to principle of increase of entropy for reversible processes, change in entropy of universe is equal to 0. And since this is a cyclic device and cyclic integral of any property is 0 and entropy is a property of system, so this is 0. So that means now this equation reduces to delta S of block 1 plus delta S of block 2 is equal to 0. Sorry, this is not a heat engine, this is refrigerator. And refrigerator is also a cyclic device, and for refrigerator also change in entropy will be 0. So now if you calculate delta S1 and delta S2, delta S1 is nothing but MC ln, because both are having mass m and specific heat both for both the cases are same because both are made of same metal. So MC ln for body 1, MC ln final temperature is T dash plus 100 divided by T, and for block 2 this is MC ln T dash by T, because the final temperature of block 2 is T dash and final temperature of block 1 is T dash plus 100. So delta S1 is this much, MC ln T dash plus 100 divided by T, and the delta S of second block is MC ln T dash by T. From this or MC ln T dash plus 100 multiplied by T dash divided by T square equal to 0, or ln T dash plus 100 multiplied by T dash divided by T square is equal to 0, because MC cannot be 0. So from this equation it is evident that this one has to be 0, or ln T dash square plus 100 T dash divided by T square equal to ln 1, because you know ln 1 is 0, or T dash square plus 100 T dash divided by T square is equal to 1, or T dash square plus 100 T dash equal to T square, or T dash square plus 100 T T dash minus T square equal to 0. And solving this quadratic equation, which is a quadratic equation in terms of T dash, we can solve this equation and find out that T dash is equal to minus 100 plus minus 633.936 divided by 2. You see, T is already given to be 313 Kelvin. So putting that value here and equating this equation, we can find out that T dash is this much. And negative values are impossible values. So T dash will be nothing but minus 200 plus 633 minus 100 plus 633.936 by 2. So this is equal to 266.968 Kelvin. Negative value are not acceptable. So this is the value of T dash, only possible value. So Q is equal to, you see, this is Q is equal to, from the diagram, you see, Q is mc T minus T dash. M is the mass, C is the specific heat, mc multiplied by T minus T dash, because the Q is the heat rejected from the body. Accordingly, Q plus W will be mc final temperature T dash plus 100 minus T, because on being added, on this block being added by a amount of energy, that is Q plus W, its temperature goes up from T to T dash plus 100. So now Q is equal to mc small c specific heat T minus T dash. So this is equal to 10 multiplied by 0.4 multiplied by 313 minus 266.96. This is equal to 184.16 kilojoule. Similarly, Q plus W is equal to mc multiplied by T dash plus 100 minus T. So this is equal to 10 multiplied by 0.4 multiplied by 266.96 plus 100 minus 313. So this is equal to 215.84 kilojoule. So W is equal to Q plus W minus Q. This is equal to 215.84 minus 184.16. This is equal to 31.68 kilojoule. So next question is question number 7.30. A body of, in fact this has already been solved in question number 14, and slight correction is required. In the question it is given that Q plus T2 work of it would be Q minus T2 multiplied by S1 minus S2. So first we will read out the question. A body of finite mass is originally at a temperature T1 which is higher than that of a heat reservoir at a temperature T2. An engine operates in infinitesimal cycles between the body and the reservoir until it lowers the temperature of the body from T1 to T2. In this process, there is a heat flow Q out of the body. Prove that the maximum work obtainable from the engine is this much, Q minus T2 multiplied by S1 minus S2, where S1 minus S2 is the decrease in entropy of the body. The exactly same question has been solved in question number 7.14, but here in the question if you go through, you will find that it is written that maximum work is Q plus T2 multiplied by S1 minus S2. Maximum work cannot be higher than Q, so this is wrong. It should be Q minus T2 multiplied by S1 minus S2, because no matter whatsoever happens, work cannot be higher than the heat input. So it should be Q minus T2 multiplied by S1 minus S2, where S1 minus S2 is the decrease in entropy of the body. So let's repeat it, although it has been discussed in question number 7.16. So it is a case of a heat engine, reversible heat engine operating between a finite body and a reservoir. This is in fact a finite body जिसका टेम्परेचर इनिशियल टेम्परेचर T1 है, और obviously its final temperature is T2, which is same as the low temperature reservoir. This is the finite body, and if you extract heat from this, its temperature will go down, and the moment its temperature reaches the temperature of low temperature reservoir, that is T2, the engine would stop working. So this is reversible heat engine. Obviously a reversible heat engine between two given temperatures produces the maximum work. So if this is Q and this is W, means this will be Q minus W. Since this is a reversible heat engine and all the processes executed by this heat engine are reversible, so according to principle of increase of entropy, delta S of universe has to be 0. And in this case, delta S of finite body first plus delta S of heat engine plus delta S of reservoir. There are three components of this universe, three subsystems. One is finite body whose temperature decreases from T1 to T2, and second one is the heat engine that completes a cyclic process, and the third one is the reservoir whose temperature remains unchanged, of course. So this is reservoir equal to 0, and this is, since this is a cyclic device, this is always 0 for a cyclic device, because entropy is a property and cyclic integral of any property is 0. So delta S of body plus, what is the delta S of reservoir here? In case of reservoir, if you calculate the change in entropy, it will be nothing but the Q minus W divided by T2, because T2 remains unchanged here, temperature of reservoir. So this is S2 minus S1. Delta S of body is, S2 is the final entropy of body, finite body, and S1 is the initial entropy of finite body. So from this equation, S2 minus S1 plus Q minus W divided by, here the temperature of reservoir is T2 equal to 0, and in fact this is W is for W max, because for reversible case work produced is maximum, and for reversible process delta S universe is 0. So from this equation what we found is T2 S2 minus S1 plus Q minus W max equal to 0. So from this equation this is obtained. So now W max will be Q plus T2 multiplied by S2 minus S1. This is in fact the change in entropy of finite body, but in the question it is given that S1 that final expression for W max is expressed in terms of S1 minus S2, not in terms of S2 minus S1. So obviously a minus sign will be put before it, where S1 minus S2 is the decrease in entropy, not change in entropy. If it had been change in entropy, it would have been S2 minus S1. So S1 minus S2 है जो decrease. Obviously here there is a decrease in entropy of finite body because there is a decrease in temperature of this finite body from T1 to T2. So obviously the change in entropy will come out in negative with negative sign. So this is nothing but Q minus T2 S1 minus S2, where S1 minus S2 is the decrease in entropy, decrease in entropy. So this is proved. So slight correction is needed. It should not be Q plus T2 multiplied by S1 minus S2. It should be Q minus T2 multiplied by S1 minus S2, where S1 minus S2 is the decrease in entropy of the body. So thanks for watching.